Hi everyone. As Yassi mentioned, I'm going to talk about the performance analysis using the Nsight System, Nsight Compute tools on A100 GPU, which means the ThetaGPU system or the Polaris system, which will come soon. And also, you have an account on the NERSC system. You may use these tools on the Perlmutter system for your application. So this is the overview of the NVIDIA, the tools overview of NVIDIA tools. So actually, the last month we had a very quick introduction of the ThetaGPU part, including the machine learning part and then tools part. So I quickly introduced this overview part last month, but I just want to remind you of some features. So NVIDIA tools package, there are several tools under the hood. The Nsight system is system-wide visualization of your application performance, and it optimizes the bottlenecks to scale efficiently across GPU and CPU on the ThetaGPU or some cluster with A100 GPU. And after getting the profile data from the Nsight system, you may see what is performance of your the application, and then you may find out some weird kernel, some kernel is underperforming or some performing weirdly, and you may want to understand what's going on that specific kernel or set of kernels, right? In this case, you can use Nsight Compute. Nsight Compute is an interactive kernel profiler for applications. So you can specify which kernel you want to profile with Nsight Compute, and then Nsight Compute can provide the detailed performance metrics and API debugging through the user interface and the command line tool. And it also provides the customizable and data-driven user interface and metric collection that can be extended with analysis script for post-processing result. The another package under the Nsight tool package is Nsight. You can see the Nsight graphics, which is a standalone tool for the graphic applications. In general, in HPC, the community, we have little chance to use Nsight graphics, but depending on your application, you may be interested in using that. But in this case, you can use it. But today, we will focus on these Nsight systems and Nsight Compute on the ThetaGPU. Before we start, so this is a simple step-by-step guide how to run the Nsight system and Nsight Compute on ThetaGPU. So on the ThetaGPU, first of all, you need to build your application for the ThetaGPU, especially for A100 GPU, right? And then you need to you need to use ThetaGPU login node to start your job. So there are a couple of ways to use to access the ThetaGPU login node, but this is one of my favorite ways. So after login to the Theta login node, if you load this module Cobalt GPU, actually your login node becomes ThetaGPU login node, right? After that, every job you submit goes to ThetaGPU partition. So after loading this module, you may submit your job to JavaScript to the ThetaGPU, or you may start interactive job mode on the ThetaGPU. So this is the example of the ThetaGPU interactive job mode. So Q-sub-I, -N1 and -T30, and this is 30 minutes, and -Q full node, or you may use a single GPU node. In this case, you will get only one A100 GPU, and then you need to specify your project code here. So to start that, for the Nsight system, you need to run with this command line. So Ansys is the acronym of Nsight system, and then profile and -O, this is alpha file name. And then -stats, it's equal to true, and then your application. So your application is some command line argument you need to put after this line, right? After this part. And then you will get the Nsight system output file, and then I will talk about how to post-process that result later. And for Nsight Compute, so as I mentioned before, after running the Nsight system, and you may have some specific set of the kernels to investigate, right? So with Nsight Compute, you can start with NCU and dash dash detailed. So dash dash set detailed, this is an optional knob. This is my preference because it provides additional information. So I always use it, but if you don't want, you can just drop it. And dash K kernel name. So if you know the exact kernel name, you can write down, you can type your kernel name at here after K. And then dash O the alpha file name, and then you need to put your application and the command line argument for your application. But many cases, your GPU kernel name is not really simple, and it's very long, right? So in this case, I recommend you to use this syntax. So instead of dash K kernel name, you may use dash K regex colon, and then you can put the multiple kernel name here. So in my demo later, I will have the triad kernel and the add kernel from the stream benchmarks. In this case, I needed to add the triad and then or and then the add. And then you can put the alpha file name, and you can collect the kernel information, kernel profiling data for that specific kernels, right? So in this command line, if you don't put the -o option, Nsight Compute provide performance data as the standard output. So it's similar to the NVProf result. So NVProf was a previous generation of the profiling tool from NVIDIA, and then for more details, the NVIDIA decided to launch the Nsight System and Nsight Compute instead of NVProf. So if you have used NVIDIA system for a long time, you probably you're familiar with NVProf, but I'll say this is a time to change from NVProf to Nsight System and Nsight Compute. And after running the Ansys and NCU, you will get the outputs from the Ansys and NCU. And there are a couple of ways to see the data, right? So if you prefer to use a text-based Linux-style output, you can use the post-processing through the CLI command line interface. And then for that, you can use these lines: Ansys stat alpha file name and NCU-I and alpha file name, and you will see all the collected data on your terminal. Maybe for younger generation, they may prefer to use the GUI interface because the GUI is their standard, right? So if so, you can install the NVIDIA Nsight System and Nsight Compute after downloading both of them from the NVIDIA Developer Tools. So you just need to create your account free, and then you can download them. And then after installing this, the client version of Nsight System and Nsight Compute, you need to download the Ansys alpha file, which is ending with QD REP and SQLite to your local system, and then open them with your client version of the Nsight System. And also the NCU alpha file name, you need to download them and then open it with your client version. Basically, I will show you several the knobs I use, but it has a lot of features. So if you are interested in more features, you may type Ansys-help and NCU-help, and then it will show you a lot of the knobs you can investigate, you can enjoy. So this is the step-by-step guideline, and we also have the corresponding information on our user guide here. So if you come to alcf.anl.gov, and then if you go to Support Center, you can find out the ThetaGPU node, and then you can find out the NVIDIA Nsight the page, and you can see the step-by-step procedure here, what happened on the ThetaGPU. So once we have the Polaris, we will update it for the Polaris as well. But for now, you can just follow this instruction for ThetaGPU partition.
J-Hook, we have
Yes?
2 questions. So
okay.
George is asking, does the regex work with NVTX annotation in the code? And then the Alfred is asking about the example of kernel name in the ThetaGPU. Okay,
so Alfred's question is easier one. So I will have the demo, so I can show you what kind of kernel name you can see on the ThetaGPU. And NVTX annotation, I didn't try with REGX work, but basically I don't see why it doesn't work, but I haven't tried it. So you can try with the REGX with NVTX annotation combination, and yeah, we can try, right? So, but sorry, but I haven't tried it by myself, but so I cannot say actually it works, but I guess it works. There is another Okay, in my experience, kernel name corresponds to name of the CUDA kernel function that is annotated with the dash global underscore global. Yeah, that's true. So depending on which program model, right? If you use CUDA, so in the stream benchmark, the kernel name is a little bit simpler. But when I use the OpenMP target uploading model with NVHPC compiler, it has some additional part, some additional part in the kernel name. So I will show you those cases. Okay.
Thanks.
Okay, so let's move on to the next one. Okay, so I just want to show you the NVIDIA website here. So if you click these two links, you can go to here, right? So this is the NVIDIA Nsight Systems website. You can see nice screenshot collected from some application, and you also have some icon for the download, right? So you can download it for your local system, and you can open it. And also, this is Nsight Compute page from NVIDIA, so you can download most recent version for you, and it also has some nice features with some description, right? So yeah, you can see what kind of thing you can use here. Okay, and it also has some detailed documentation here, so you can find it out. There are a lot of information over there. So I just show you some tiny piece of the part of feature today. Okay, so actually, so if you look at the documentation from NVIDIA system, you can see all the details, right? So, but the problem is for beginners, sometimes too much information is not very useful, because sometimes we cannot find out where we can start, right? So because of that, today's the session, I just want to share a couple of the HPC benchmark cases, and then what kind of information I see, and how to interpret those information for the application. So this is what I want to try today. So first case is a stream benchmark, which is popular HPC benchmark to measure the memory bandwidth, right? So stream benchmark was developed originally for the CPU, and then the University of Bristol team extended the stream benchmark to the other programming models for the GPUs and other FPGA and other devices, right? So if you go to this GitHub repository, you can download the entire package of the Babel stream. They call the Babel stream. And then this Babel stream includes the stream benchmark implemented multiple programming models. So so as you know, we have a lot of different types of the architecture, right? So even on the CPU side, we have x86-based CPU and the ARM-based CPU. And GPU side, we have NVIDIA GPU and AMD GPU is coming, and Intel GPU is coming. We also have FPGA, the architecture for HPC, right? So for that, because of that, we have a lot of the different programming models, and Babel stream has CUDA implementation, OpenMP threading, OpenMP target uploading implementation, and SQL, which is another open source, the portable programming model, and HEAP, and OpenCL, and Cocos, and Raja. Most of them will work fine with the Nsight system, but unfortunately, NVIDIA systems, NVIDIA Nsight system and Nsight Compute does not support OpenCL programming model. So if you use OpenCL model, unfortunately, you can run your application on the system, but unfortunately, you cannot collect the profiling data from the tools. So sorry about that, but okay. And then here, we can choose the CUDA implementation, OpenMP target uploading implementation, or SQL implementation on the ThetaGPU, but this is NVIDIA systems, so I just want to try the native CUDA implementation for A100 GPU. So, and the Babel stream, the stream benchmark, it has basically 5 main kernels to measure the memory bandwidth for a given array, a size of n. So first one is copy kernel. It basically just runs CI is equal to AI, A of i's of A, right? So so here, if you see how many plot operation, floating point operation in this line, we don't see anything, right? You just copy, right? So we have a 0 plot for this line. And how many data transfer we have in this case? We have 1 read for AI and then 1 write for the CI. Because of that, we have 2 data transfer And if we use a double precision, we can say this is a 16 byte. And then if we run for the array size n, you can say 16 times n bytes data transfer happen for this kernel, right? And the arithmetic intensity is defined as a ratio of the flop over byte. So based on this definition, you can say the arithmetic intensity is equal to 0. The second kernel is mul, which is a multiply kernel. And basically B is equal to scalar times CI. So here we can see one floating point operation. So one multiply instruction happen here, right? So for this case, we can say the total number of flops is n because we are solving for the n array. And then we have one read for the CI and then one write for the BI, right? So you may ask why we skip the scalar. So scalar is a scalar, so it just stay in the register, so it does not require additional data transfer for repeated the repetition of this kernel. So because of that, in general, we can say we have only one read and one write. So as a result, we have the 16 bytes times n, 16 times n bytes data transfer is this merge kernel. And then the flop over byte ratio is n over 16, so it is around 0.063. And the major instruction of this code is MUL instruction. This is a multiply instruction. So add kernel is C is equal to A plus B. So again, we have one add instruction, so number of flop is n. And the data transfer is different from the mul because we have two reads, A and B, and then one write, C. So 24 byte times 24 times n bytes data transfer happen. Because of that, arithmetic intensity become 0.04, and the major instruction is add instruction. So fourth one is triad, which is A is equal to B plus scalar times C. So we can do the same thing, right? So now we have one add and one multiply as a result. We have a 2 times n flop for this kernel, and we have 2 read and 1 write, so 24 times n byte, the data transfer happened. And as a result, arithmetic intensity is 0.083. So that product is a little bit more complicated than the others because it has reduction operations. So, but anyway, you can do the same similar using some similar approach. So we can say the number of flops is 2n and the byte is 32 n byte. And the arithmetic intensity is 0.06, and the major instruction is FMA, fuse the multiply and add instruction. So this is a screenshot of the add kernel written in the CUDA. So as you see, we have the index I computed by the block DM and the block IDX, which is part of the CUDA part. And then we do the C is equal to A plus B, right? So the triad kernel, we do the same thing, right? So we compute the index for the kernel, and then we do the A is equal to B plus a scalar times CI. So basically in this demo, I will just collect the kernel data from the add kernel and the triad kernel, and we will see some details. So Nsight System with the stream benchmark, this is the exact command line I ran, and so let me show you what happened on the demo here, right? So I grabbed the one GPU, ThetaGPU node here. So here I already built the application. So CUDA stream is the executable here. So if I run it, this is a standard output of the CUDA stream. And as you see here, this benchmark is to measure the memory bandwidth, right? So the copy, mul, add, triad. So you can see for 5 different kernels, we can see around 0.2 to 0.3 teraflop per second of the memory bandwidth. Since this is HBM2 memory, so it's very fast, right? So we can measure the memory bandwidth. And then if you want to run the Ansys, yeah, I just want to avoid some typos. So I just want to copy and paste here. So in order to run the Ansys system, Nsight system, you can just run it here. So Ansys and profile -o and the file name, and then -stats is equal to true, and then just run your application here, right? So if you run it, yeah, so warning, so we can ignore that. And then you can see the standard output from the original application. After that, you see some profiling data as a standard output here, right? So you can see the CUDA API, the CUDA Mellow happen, CUDA Synchronize happen. And the kernel statics, you can see we have the 6 kernel. I told you 5 kernel, but it has some initialized kernel here. So we have add, try the dot, merl, and the copy kernel, and then initialization kernel, right? So mainly we have 5 kernel, and we see the memory operation. This is the mem copy from device to host, and then we also have some kind of row level OS runtime API statics. So if you're a Linux crew, you can see a lot of information from here, but not from me. Okay, after running that, you will see the Ansys generate this 2 file as an output here. And then you can download it to your local system. So to save our time, I already downloaded. So I just started the Ansys. So if you open the Ansys on your local system, you can see this kind of the white page here. And then I already downloaded it, and I think this is the result here. Okay, so this is some warning. And this is first page you can see here, right? So on the top, you can see the CUDA hardware, and the bottom you can see thread. Thread means CPU, so we are not very interested in CPU, so I just reduce the size. And then in the CUDA side, we can see the 2 blocks, kernels and the memory here, right? So if you open the kernel, you can see the 5 different kernels here, and then also 1+ initial kernel. And for the memory operation, you can see the D2H mem copy, right? And then on the kernel, if you're on the right-hand side, if you click the right button, and then you can see the show event and view here. And then at the bottom, you can see all different kernels you ran on the GPU side, right? And then if you click one of them, try the kernel, it provides what is the begin time, end time, and the grid size, the block size, and some other information, right? So local memory total and local memory thread, etc., right? And you can also zoom in, see what's going on here. So zoom in the selection, and you can also use your memory to extract, right? And here you can see, okay, the add kernel happened, and then try add kernel, and then the dot kernel, and there is some data transfer here, and copy kernel, and more kernel, etc. So this kind of pattern is repeated because this benchmark will repeat 100 times for each kernel. So this is the quick demo of the Nsight system. And then for some reason, I see, okay, I just want to see what's going on in the add kernel and try the kernel. If so, you can run it with the NCU. So I also here. So can you see my screen? It's just hide it, right? Let me use it. Okay. So here I put the NCU -h set detailed, and then -o and file name, and then -k regx, and then I added the triad and the add, right? So previously, okay, and then so if I use regx, I don't need to specify the entire kernel lane, and then I just run the CUDA stream. So if I run it here, it start the application. And then you can see add kernel, try the kernel, add the kernel, try the kernel, right? So what you see here is NVIDIA's compute. In order to collect all the required performance data, NVIDIA compute smartly manage the launching the kernel. So when you launch this kernel, it has some image of your memory space, and then for this specific case, it repeats the kernel launch for 18 times without changing your numerical result. So it's a very smart way. But the another way, since in order to collect all the data, Nsight Compute repeat your kernels, in this case 18 times, right? Because of that, your execution time become much longer and longer, right? So if you have some application with a lot of kernels, and if you want to see, if you decided to see all the detailed kernel information with NCU for your entire application, it may not be really great idea because you have to be ready for a lot of the overhead, right? So because every your kernel will be executed 15 to 18 times to collect the performance, and then each overhead is really huge. So it takes quite time. So I already downloaded the NCU report on my system. So let me go back to, okay, here. So this is a NCU client version on my Mac. And then we can open file here. So I already downloaded it somewhere. NCU, try it here, right? So, okay, I downloaded it here. Oops. Okay, something here. So this is your starting page of your report. So here you see the summary page here, and then you see all the function name you collected. So I specified add kernel and the tried kernel. So you can see the all add kernel, tried kernels are repeated 200 times, right? Until 1999, right? And then if you go to detail here, and you can see multiple panes, and if you extend it, you can see the GPU speed of write throughput. So basically what it shows is what is your the SM utilization, what is your memory utilization, right? So here, this kernel, as we know, the stream benchmark is to measure the memory, the performance of memory subsystem. Because of that, your SM utilization is not really high, right? This is the intentional thing, right? So, but the memory throughput should be very high, right? So here, what you can see here is, okay, so I I previously added the baseline. Let me clear it out. Okay, so here you can see the SM utilization is the 6% and memory utilization is the 89%, right? And then you can also see the two columns for details. So this part is SM details. So SM instruction active, executed, etc. And right inside, this is detailed information about your memory subsystem. So here DRAM active ratio is 89% and L2 T section ratio is 52%. So you can see the details here. And then we use the dash set detail that we can see the what is the roofline analysis data here. So on the roofline analysis, we have two axes. X-axis represent the arithmetic intensity, which is plow by ratio. And then Y-axis represent the performance in plots, right? And in every system, we have two roofline here. So we have inclined roof and then the flat roof here. So, and this part is a machine balance point. So if your the arithmetic intensity is less than this balance point, what you can say is that your kernel is memory bound kernel. And if your the plow by ratio is larger than this machine balance point, we can say your kernel is compute bound kernel. So in this case, obviously we are measuring the memory bandwidth. So our kernel is supposed to be memory bound kernel, right? So, and then our kernel hit the roof line of the memory bound kernel, right? So we can say this even though the plow rate is much less than the theoretical peak plow rate of A100, we can say this is a very well optimized kernel because it touched the memory bound roof, right? Then what it says, that means your code fully utilize your memory subsystem, right? So, and here its arithmetic intensity is 0.04 and the measured plow rate around 60 gigaflop per second. If you go down here, you can see additional details. What is pipe utilization? So this is LSU, so load and store unit. So basically, this is memory bandwidth measurement. So load and store unit is the major the unit we use, right? And then if you go down, you can also see the warp scheduler utilization and also warp state statics. So here you can see the store long scoreboard is very high, right? Which means for this instruction, it takes around more than 200 cycles, right? So what happens? So in general, your CUDA cores are much faster than your memory subsystem. Because of that, if you have to have some data from your memory subsystem, your CUDA cores wait until your memory transfer is completed, right? So we call that stall. So since the CUDA cores are much faster than your memory system, and then your memory, your kernel mainly waiting for your memory data transfer, it says your store, the cycle for this store long scoreboard is very high, right? So this is expected because this kernel is for measuring the memory bandwidth, right? So That's that. And also we can see what kind of instruction executed, right? So IMAD, this is basically the integer multiply and add. And then we have some kind of move operation and the de-add operation, because this is add kernel, right? And then we have also register counter and the block size and etc. So this is a kind of detailed information. And if we change it to the triad kernel, in general, it's almost same. And you can see the memory, the loop line twice is a little bit different because we can compare it. So in the NCU, you can compare the multiple kernels under a single execution. So here, we previously see the add kernel here, right? And then if I add baseline here, you can see the baseline, and then this is add kernel. And after that, if you click the another kernel, triad kernel here, now the green one represent add kernel you selected before as baseline, and then blue one become your current kernel, which is triad kernel, right? So if you want to compare what is difference between the add kernel and triad kernel in the loop line, you can see these two lines here, right? So this is the green markers represent the add kernel, and the triad marker you can see it represent the blue marker represent the triad kernel, right? As you see here, the measured arithmetic intensity for the add kernel is 0.04, and the measured the triad kernel, the arithmetic intensity is 0.08, right? If we go back to our slide here, so this is a theoretical arithmetic intensity computed by this source line, right? So add kernel we had 0.042, and triad kernel we have 0.083, right? So the measured one is 0.04 and 0.08. So we see these numbers are very consistent with the measured one, right? So we can trust this tool. And then if you use this baseline comparison, you can also compare some other cases right here, right? So in both cases, the SM utilization is low and memory utilization is high. And also it's very similar, right? Because they are mainly measuring the memory bandwidth, right? So basically, they are very similar to each other. The only difference I would say is, yeah, we cannot see, oh, here, only difference here is for the blue line, which is the triad kernel, we have DFMA, which is the double precision diffuse multiply add instruction. And you don't see the green bar here because add kernel does not have FMA instruction, it just have add instruction, right? So it is one difference. And if you go to the source here, you can see the detailed the assembly, I mean machine code here. So now we are looking at the triad kernel, right? So this is simple kernel, so we don't have a lot of lines here. So you can see this line, and then what you can see here is, okay, this line spend most of the sample count. The sample count means it has the NCU has some frequency to collect the samples, right? So if you have more sample count, which means that part spend more time on the system, okay? So it has more than 62,000 sample kernel, and that line is DFMA, right? And then if you see here, you see this is kind of the brownish one, and then the 99.89% is long scoreboard, which means it's stalled, which means they're waiting for the data transfer from the memory subsystem. If you go to the add kernel here, you see slightly different here, right? So here, again, this line, the add, spend most of time because it has the highest sample count. But previously it had the de-add, a DFMA, but now for add kernel, we have de-add, which is a double precision add instruction, right? So this is only difference. So I think this is for stream benchmark. We already show how to use a stream with Nsight and how to run the Nsight Compute. And I explained this one. And I explained this. Yes?
We have two questions. So one is, can you map the assembly to the actual line in the source code?
Yes, we can do that. So in this case, I didn't match that, but yeah, yes, we can do that. So if you add a debug symbol on your build, and then if you run it, you can see the source line on the left hand side, and then right hand side you can see the assembly. Yeah, you can do that.
And then the other question is, what assembly is this kernel compiled to?
So I think the SASS is assembly name. So I'm not the expert on the assembly, but in my understanding, if you use a compiler on A100 GPU, they use MBTX some format, and then that becomes the SASS assembly, in my understanding. I may be wrong, but yeah. But whatever your frame model, you can. So if you run your application on the A100 GPU, basically you are using the same assembly on the system.
So a follow-up question is, would that require both -G and -G plus the line info in the command line?
Yeah, so it depends on depending on your compiler, they have different options how to provide a debug symbol, right? So the CUDA compiler MBCC and the NVHPC compiler MBC and the NB CPP, both of them has a different options. So you need to check what kind of compiler flag is required for the compiler you're using. But in general, I can say -G and -G line info, it could be enough, but yeah, you need to check it.
Thank you.
Okay. Okay, so this is the example demo for the stream benchmark, and then let me move on the next case, right? Okay, so I showed the running the terminal and reviewing report and the kernel CUDA operation, running terminal review. Okay, and I showed the baseline, how to use baseline for comparison, right? And the single execution, and I talked about the arithmetic intensity and the add FMA instruction. Okay. Let's move on to the next case. This is another simple benchmark for the geometric series computation. So geometric series is basically this computation, right? S is equal to 1 plus R plus R squared, R cubed, and to the R to the NGO, right? And as input parameter, we have N square array, and then NGO is given as an input. So this is order of geometric series. And then the benchmark create the n square array with ratio, and then initialize with the positive number. This is kind of initialization process. And after that, we repeat 100 times to compute the geometric series with the given NGO. So A100 GPU, we have a couple of options to build this. So we can use NVHPC compiler from NVIDIA. Previously, it was a PGI compiler. So PGI compiler was well-known compiler for OpenACC, and they extended it to OpenMP target offloading. So we can use NVHPC compiler. And another option could be you can use a Clang compiler, which is also Clang also can enable the GPU offloading with the OpenMP target offloading. So that can be one choice. Another choice is recently the Gmans also developed the GCC compiler with OpenMP offloading. So we don't have GCC compiler on our system though, but yeah, if your system has a GCC compiler, you may use a GCC compiler for OpenMP target offloading. But in this example, I choose NVHPC compiler because this is provided by NVIDIA. And for to build it, I use MVC compiler with this option. And then this is the kind of main part of the compute GEO kernel. Okay? So I use OpenMP target offloading. So using the OMP target pragma, I offload this kernel to GPU, A100 GPU. And then this for loop is about the loop for the different components, right? So n square array component, right? And then for each component, we have one read one variable. So we read the ratio, and then we repeat this FMA instruction to the NGO. So in order to compute this geometric series, the kernel just repeating this process, right? So here we have one addition and one multiply, which is one FMA instruction. And then finally, we can say the NGU times FMA instruction happen in this kernel. After that, we save the result to the global variable. So we have one write variable, right? So based on this computation, we can get the theoretical arithmetic intensity here. So basically, we have one read and one write. So we have 2 times 8 bytes. So if you use double precision, you can say the 16 byte happen for a single kernel. And then we have 2 times NGU because this loop is repeated NGU times. And then at each loop, at each execution, we have one add and one multiply, which is one FMA instruction, which is 2 plus, right? So as a result, we can say the theoretical arithmetic intensity is 2 times NGU divided by 2 times 8. So basically, this kernel, depending on the NGU number, its arithmetic intensity changes, right? And then without the NCU and Ansys, I just ran it on the A100 GPU, and then the benchmark itself provides what is the measure the word time and then the computed plus based on the theoretical flop count, and then this is the result. So I just chose this one array size 8192 square array, and I use the double precision and I use the single precision. And then I use 4 different NGO with the 10th order, 100, 1000, and 10,000, right? And I repeated the same thing for the single precision. And this is measured word time. And then based on this measured word time, we can compute what is flop rate of the kernel. And then I computed the efficiency based on the theoretical peak performance. So A100 GPU on ThetaGPU, A100 GPU on the ThetaGPU partition, its peak double precision flop rate is 9.7 teraflop per second if you don't use a tensor core. And for single precision, the peak is 19.5 teraflop per second. So based on that theoretical number, I just computed the efficiency. So if you use NGU 10, for double precision, its efficiency is around 16%, right? And if you use the 10,000, it is 99.54%. This is very high, right? But we are doing the same kernel, but for some reason with this kernel, it got almost 100% efficiency, but in this case we got very low efficiency, right? So I'm curious what happened, what happens in this kernel. And the single precision, similar trend happened, right? So 10, it takes 9%, and the 10,000, it takes 92%. So basically what happened on the double precision and single precision are very similar to each other. So I just decided to investigate what's going on with double precision. And then again, the Nsight system with the NGO kernel, we can just run it. So I can show you how it goes. So basically the benchmark itself is here. So if we run the OpenMP, DP, and 10,000 case, right? So if you run it, this is a standard output. So I just made some silly mistake on the build, so you can just ignore this part. So it just ran it, and the matrix size is 8192 square, and the order of geometry is 10,000, and then repeated 10 times after one warming up. And this is size of the memory, and then the benchmark report what is flop rate of this kernel, right? So 9.5, which is very high. So in order to run the Ansys, I just put it here. So let me just copy and paste here. So if you run here, it will start soon. Okay, please ignore this warning. And then you see the standard output. After that, it provides the data here, right? So here, CUDA API, we have a lot of time spent for the CUDA stream synchronized. And here we just have only one kernel, compute GEO kernel. So there was question about the kernel name here, right? Since we are using NVHPC compiler for that reason, NVHPC compiler add this NV kernel underscore before the kernel name. And after that, it adds some weird numbers, which I didn't generate it, but generated by the compilers. It happens all the time, right? So this is actually kernel name. So if you use NCU-K kernel name, you have to write down this exact kernel name. Or if you use regex, you can just put some keyword of a compute GEO here, right? And then it has some memory operation from host to device and device host. And then we have the OS runtime API here. So if we go to the Nsight system, I downloaded it before. So this is one of them. Okay. So this is the result here. So you can see we can ignore the CPU part and we can extend the GPU part and we can extend it here. So if we open the kernel, we have total 11 execution here, right? Because in the benchmark, we have some one warming up process, and then we have some repeated process. So for some reason, okay, here, as you see here, so warming up just takes around 180 milliseconds, but after warming up, the word time reduced and become very consistent, right? It is why we use warming up. So it has 11 kernel execution, and each kernel execution, we can see the grid size and block size, right? And then to run the NCU with the application, I ran it. So NCU set detail, and then I put the -k, RGX, and the compute underscore. This is part of the kernel name, right? So I don't want to specify exact name. And then put the alpha file name, and then run the application here. So if you run it here, again, warning, and then it will show the application here. So, and then you see here the NV kernel compute collected before this string, right? So this is actually the benchmark run the warm up process before running the actual execution. So we have 1 execution before this message, and then the 10 execution for the measurement after the warming up. And then you can download it. I download it to my system so I can open it up. So actually, I ran the 5 different cases for NGO 10, 100, 1,000, and 10,000, right? So I already have that data here. So we have 10. Okay, something will happen. Okay. And then now we are dealing with the multiple executions. So we can open the multiple NCU file here 100 times. And macOS works weirdly. Okay. And then I would like to open the last one, the 10,000. Open here. Oh, what happened? Okay, so here you can see 4 different reports here, right? So 10.ncu and 100.ncu and 1,000.ncu and the 10,000.ncu. So I ran this these 4 executions before this demo. And then you can see the summary. We have 11 kernels from 0 to 11 because it has one warming up process. And then if you go to detail here, and then we can extend it everything here, right? So let me clear everything. And then let me add it. So I go to here and add base. So baseline 1 is about the 10. And here, detailed, and add base. So purple represent 1,000. And then if I go to detail and add base, so orange represent the 10,000, right? And then if you go to first one, you see the blue one is for NGO 10. This is NGO 100, 1,000, and 10,000. And if you go down here, you can see the speed of write throughput here, right? So if you look at this one, so blue one, which represent NGO 10, we have SM utilization is around 50 to 60%. But the 10,000 case for orange case, we almost hit the 100, right? And the memory operation for NGO 10, we have around 78% memory throughput. But for orange one, our memory utilization is very low, which means the first NGO has some kind of a lot of the compute operation and the memory operation, right? Both of them. And the orange line, which is NGO 10,000, we have a lot of computing operation and we have very minimum memory operation. So in general, your core is much faster than memory subsystem. So if your kernel use your core more frequently, that means you can get the higher flop rates, right? So that's what we are seeing here. And then if you look at the roofline plot here, you see here, so this one is the NGU 10, 100, 1000, 10,000. So if you go back to our slide for this case, so this is a theoretical the arithmetic intensity here, right? So the AI is 2 times NGU divided by 16, right? So if you compute that, this is actually the computed theoretical AI 1.25, 12.5, 125, and 1250, right? And this is measured AI by the NCU, so 1.33 and 12.68. So there are slight difference, but overall we can say they are very consistent to each other. And then this is measured cloud base. So from here, we can see since kernel has a different arithmetic intensity based on the NGO, the order of the geometric series, on the roofline, it shows the different AI number here, right? So what happened in NGO 10 is since this NGO is low enough, so this kernel is memory bound kernel, and then it used very high memory subsystem utilization. As we increase NGO number, it becomes the compute bound kernel, and then we can get the very high clock rate here, right? And then we can also see the pipeline difference, right? So ALU is this is for the arithmetic logic unit. For this is for bit manipulation or logic instructions. This is basically for the loop style, right? And then it has FP64 instruction, right? So since we have less number of FMA instruction for the NGO 10, we have less utilization on the blue line, which is NGO 10, and very high utilization with the orange line, which is NGO 10,000, right? And if you go down, the scheduler is similar. And here, this is a interesting part. So previously, when we talk about the stream benchmark is to measure the memory bandwidth performance, right? Because of that, intentionally, the kernel could have the high stall ratio, right? So in this case, we have less operation, less FMA instruction per data transfer. We have a higher stall cycle here, right? And compared to the orange one. Orange one has a very localized repeated computation happens, so the store ratio is very low. But in this case, the store ratio is relatively high because of the data transfer. The kernel is waiting for the data transfer completion, right? And another way, so here, if you look at the math pipeline throttle, so which means we use a lot of FMA instructions. So the orange one has the higher the higher number in this case. Again, this is executed the instruction mix, right? So DFMA is the double precision, the fuse multiply add operation. So it has a very high number in the orange line here, right? And we can also see this one on the source code here. So if you go to SAS here, this is NGO 10. So it shows every line of your assembly. And then what you can see here is, okay, you can see here is if you go down, you can see some high part here, right? So D-add is high part, right? And then if you click here, this is a kind of the brownish color because of it is very high stall ratio. And if you go to NGO 10,000, we can do the same thing. And then if you go to source line here, and if you see the SAS, you can see, go down. And here we have different idea, right? So we have, since we are using the same kernel, so it should have FMA, DFMA part, but since the kernel is waiting for the data transfer, so this part, the sample data is not very high here, right? But for NGO 10,000 case, in this case, the kernel mainly use DFMA, and then you can see a lot very high the sample data, and as you can see here, the mass pipeline throughput is at 68%, which means most of FMA is working with the 68%, right? And then it has some kind of weight and some kind of unselected one, but mainly compared to this brownish color, we can see this kernel is more active in the computation, right? So this is the difference what happened for the same kernel for different input. We can see the performance difference, and then using the NCU tool, you can see more details in the assembly and loop line and other instruction based data, right? So I think this is I think we have just 3 minutes, right? I think this is all I have. So we talked about all the details